Good afternoon, everyone. My name is Alwan Anugrah Gani, and together with my colleague, Syed Shahril Sazani, we are pleased to present our proposal for assignment 3 of the Advanced Concrete Technology course. Under the guidance of Associate Professor Insinyur Dr. Norazzlina, we have developed a durability-based foundation improvement proposal. Our primary objective is to engineer a guaranteed 50-year life cycle for a proposed three-story reinforcement concrete academic building. In engineering, we often focus solely on bearing capacity. However, today we will demonstrate why geotechnical stability and concrete durability are two sides of the same coin, especially when dealing with problematic ground conditions. Let us begin by looking at the battlefield, our site profile. We are dealing with a classic but challenging geotechnical scenario. Our site investigation reveals an 8-meter thick layer of highly compressible soft clay. This layer is characterized by low shear strength and poses an extreme risk of long-term primary consolidation and, more dangerously, different settlement. Beneath this clay lies our bearing stratum, a dense sand layer. However, the soil isn't our only adversary. We have a shallow water table at just 1.2 meters below ground level. Chemical analysis of this groundwater shows moderate sulfate levels and slightly acidic pH levels. This presents a triple threat. First, the geotechnical threat, which is the unstable excavations and settlement. The second, the durability threat, which is external sulfate attack and reinforcement corrosion. And the third, the construction threat, which is the highest hydrostatic pressure during the foundation works. Simply put, if we don't address both the soil and the chemistry of the sites, our 50-year target is impossible. Why are we linking foundation and durability so closely? We call this the coupled interaction loop. Traditionally, a geotechnical engineer fixes the settlement and the materials engineer fixes the concrete mix. But on this side, they are interdependent. If the foundation undergoes differential settlement, it induces tensile stress in the RC, ref, or beams. Concrete is weak in tension, so it cracks. Once you have structural cracks, the low permeability defense of your concrete is breached. This provides a highway for acidic, sulfate-rich groundwater to reach the reinforcement. The resulting sulfate attack the corrosion, cause expansion and spalling, which further weakens the structure, leading to more movement. Our takeaway is clear. A stable foundation is useless if the concrete degrades, and durable concrete will eventually fail if the foundation cracks it.
To find the best solution, we conducted a weighted multi-criteria assessment. So we compared a conventional rough, deep cement mixing along bore piles and our recommended solution, a pile rough integrated with DCM. A conventional rough fails because it cannot handle the 8-meter clay consolidation. Full pole piles are effective but highly resource intensive and expensive. Our integrated hybrid approach uses DCM to treat the upper soft clay layer. This creates a high stiffness composite grid that provides uniform support to the end rough. So we then strategically place end bearing piles that extend through the clay into the dense sand So in this system, the piles act as settlement reducers rather than carrying 100% of the load. This interaction between the treated ground, the piles, and the rough optimizes material efficiency and significantly reduces the embodied carbon of the foundation. Now, let's look at the concrete itself. To resist the acidic sulfate environment, we move beyond just selecting cement. We adopt a defense in depth strategy. First, we target a low water to binder ratio of zero point 0.4 or less to restrict capillary porosity. Second, we utilize supplementary cementitious materials, specifically GGBS or fly ash. This refine the pore structure and reduce the clinker content, making the concrete chemically more resistant to sulfates. Third, we specify a strict 75 mm concrete cover and a continuous waterproofing membrane. So we believe waterproofing is essential, which serves as the primary barrier to sever the transport pathway of groundwater. During construction, strict QA protocols are non-negotiable, verifying cover depth before pouring and ensuring rigorous curing to achieve the intended dense microstructure. An engineering solution is only as good as its verification. We have designed a 10-year preventive maintenance and monitoring schedule. We are transforming the foundation from a static object into an actively managed ecosystem. We will install settlement markers, piezometers to monitor groundwater shifts and crack gauge. Our timeline is divided into phases. For the years 1 to 2, focus on early consolidation and establishing baseline data. Year 5, a mid-life engineering review involving non-destructive testing of the concrete. For the year 10, a holistic review of initial design assumptions against a decade of actual behavioral data. So, by monitoring these parameters, we can differentiate between minor shrinkage cracks and active geotechnical shifts, allowing for surgical interventions if necessary. Sustainability in this project is defined by structural material efficiency. By using the pile rough plus DCM approach, we minimize the quantity of bore piles, directly lowering the carbon footprint. Furthermore, we've prepared a rehabilitation workflow. If a defect is detected, we follow a diagnose, stabilize, repair, protect sequence. So we don't just patch cracks, we identify the root cause. If the foundation is moving, we stabilize it first, perhaps via grouting before repairing the structural concrete. True sustainability is balancing the initial green materials with long life durability. Preventing one major repair 20 years from now saves more carbon than any specialized cement can offer today. In conclusion, engineering for problematic ground requires a paradigm shift. We must stop viewing structural fixes in isolation. Our proposals offers geotechnical synergy through the hybrid foundation, chemical defensibility through advanced binder technology, and auditable lifecycle management through our 10-year monitoring plan. By integrating these disciplines, we can confidently guarantee that this academic building will serve the university for its intended 50-year lifespan and beyond. Thank you for your time. To summarize, our proposal is based on one fundamental principle. Achieving a 50-year service life requires us to address both geotechnical stability and concrete durability simultaneously. Our site presents several major challenges, including an 8-meter layer of soft compressible clay, low shear strength, potential differential settlement, a shallow water table, and groundwater with moderate sulfate content and slightly acidic conditions. These risks are not independent. Foundation movement can cause cracking in the reinforced concrete structure, while these cracks can allow aggressive groundwater to reach the reinforcement and accelerate deterioration through sulfate attack and corrosion. Therefore, our proposed solution combines foundation improvement, appropriate foundation design, durable concrete materials, crack control, and long-term monitoring and maintenance. The key message is simple. A strong foundation alone cannot guarantee durability, and durable concrete alone can prevent foundation related failure. By treating soil stability and concrete durability as one integrated system, our proposal aims to provide a safer, more reliable, and sustainable 50-year solution. With that, we will now proceed to our proposed foundation and durability improvement strategies.